Hello, students. I've gotten quite a few questions concerning some of your web work problems, so I figured that I would take this opportunity to go through a couple of those web work problems with you. Let's take a look at the first example. That is, the following is a geometric series. Let's identify A and R, and then determine whether the series converges. If it converges, find its sum. Okay, so now let's take a closer look at this geometric series. I'm going to write it out like I did in class. You know how I like to simplify things a little bit? So this infinite series runs from n equals 0 to infinity. And what I want to start by doing is I want to start by breaking up those exponents where there's a sum or difference. And look at it just a little differently. So let's do this. Let's take -1 to the n plus 1 and instead rewrite that as -1 to the n times -1 to the 1. Like bases, add exponents. And instead of 2 to the 3n, isn't that just 2 to the 3 to the n? Or if I like, 8 to the n. 2 cubed is 8. So I'll even go one step farther, and instead of writing 2 to the 3 to the n, let's just go ahead and write that as 8 raised to the nth power. And then 9 to the 1 minus n, well, that's going to be 9 to the 1 times 9 to the negative n. And actually, what can I do with that negative n? Well, whenever there's a negative exponent, remember, that can take the things in the numerator and bring them down into the denominator. And so actually that 9 to the negative n can come down to the denominator as 9 to the positive n. And I think I'll do that as well. And get rid of that part. Okay, so now I kind of see my pieces. Let's break it up a little farther. And let's put all the nth terms together and all those extra factors or the constant factors together. And so notice we have a -1 to the 1 and a 9 to the 1. And those two can get put together as just my constants that are being multiplied by. And now I've got -1 to the n times 8 to the n over 9 to the n. And this helps me to clarify and see that this is an indicator of a geometric series, right? The n is appearing as exponents, and just exponents in this problem, a key indicator that I have a geometric series. Okay, so I'll do one more step to simplify right here. And that is, I'll put together my -1 and my 9. So let me rewrite this as the infinite summation or the infinite series n equals 0 to infinity of -1 times 9 is -9. And then how about if I put all of my other terms together with the nth power on it? So that'll be -1 times 8 or -8 over 9 all raised to the nth power. That's a lot cleaner for me, and that helps me see what I'm looking at. Now, to actually get the terms of A and R and identify what they are, I'm going to list out the terms of my series. And I'm going to start at the first term, which is when n is 0. And so when n is 0, I can see clearly that I have -9 times -8 over 9 to the 0th power. And this is when n is 0. This is my first term. And now I want to go when n equals 1 and look at that term. So when n is 1, I have the same pattern. I have -9, but this time I'm multiplying that times -8 over 9 to the first power. And then my next term when n is 2, and that's going to give me -9 times -8 over 9 to the second power, etc., etc., etc. So let's list out what we've got going here. So what we have is in the first term, I have -9 times -8 ninths to the 0th power, but I know that anything to the 0th power is just 1. And so this is just negative 9. So my lead term is negative 9. And my next term is negative 9 times negative 8/9, or that's actually just positive 9 times 8/9. And then I'm going to have negative 9 times a positive 64 over 81. And so that's going to be a negative. Actually, I should undo that. So that term is going to be a negative 9 times 64 over 81, etc., etc., etc. So this is my geometric series. Now the question is, what is my A value? Well, we learned in class that A is actually your starting value when you list out your geometric series, right? A plus A times R plus A times R to the second plus A times R to the third, etc., etc., etc. And the geometric series is created by taking this ratio that we're multiplying by on each term, this common ratio. And so for my problem, it's very apparent to see that the A term, the first term, is just negative 9. And that is getting multiplied through each term afterwards. So A is negative 9. Now the R value, well, it would probably have been better, and let me do it this way. It would probably have been better if I had kept the negative on the 9 and the negative on the 8 to show, first of all, that my A term each time is negative 9. But secondly, it shows me what I have to multiply by to get each term thereafter, right? So if I'm looking at this right here, I have negative 9 as my first term, my A value, and the second one is going to be A times R. So I have my A value, but this has to be my R value. My R value is the thing that gets multiplied. And if I take that and square it, well, sure enough, negative 8 over 9 squared is 64 over 81. So each time I'm multiplying by a factor of negative 8 over 9, so my R value is negative 8 over 9. So far, so good. So now I have identified my A, I've identified my R. Now, how do I know if a geometric series converges? A geometric series converges if the absolute value of R is less than 1. And my R value being negative 8/9, if I take its absolute value, gives me positive 8/9. That's less than 1, and that means that my series is going to converge. So everything is looking beautiful. So far, I've answered the first question, what is A and R? And then I've answered whether it converges, and if it converges, it has a sum. So the very last piece of this homework problem is to calculate the sum. To calculate the sum, we want to use our formula S equals A over 1 minus R. For my problem, A is negative 9. R is negative 8/9, so I have to be very careful that I put a negative 8/9 in there. Or in other words, negative 9 over 1 plus 8/9. And if I do a little bit of math, that's negative 9 over 9 plus 8 over 9, is going to give me 17. I did it again. Is going to give me 17 over 9. And when I flip and multiply, I think that gives me negative 81 over 17. That means this series adds up to, or converges to, a sum of negative 81 over 17. So let me summarize my results in the box. So the following series, geometric series, has an A value of negative 9, an R value of negative 8/9. Because the absolute value of negative 8/9 is less than 1, my series converges. Therefore, my series converges. And finally, I know that the sum of my series is simply A over 1 minus R, or specifically, my sum is negative 81 over 17. All right, so that's that web work problem. Let's take a look at another one. So example 2. Find the values of x for which the following series converges, then find the sum of the series for those values. So again, I want to start by rewriting this series, and this is the series n equals 0 to infinity of x minus 3 to the nth over 6 to the n. Now what I'm going to do is, like before, I'm going to kind of simplify it down a little bit just to help me out a little bit. And x minus 3 to the n over 6 to the n can be put together as x minus 3 over 6 to the n. Now, that just helps my brain see it. And I see that the n's are only appearing in an exponent, hence the clue that it's a geometric series. And I know when I have a geometric series, well, they converge provided that the r value is less than 1. So my first job is actually going to take this geometric series and expand it. Now notice, there's something different than anything we've done before. There is a variable in this series. It's an x. Now we haven't yet talked about these series, but we're just going to keep x as a variable. And we are going to list out, as we did with the last example, the first 3 terms for this geometric series. That is, I'm going to let n equal 0, then I'm going to let n equal 1, then I'm going to let n equal 2, and I'm going to see what I have coming out to play in this geometric series. So let's let n equal 0. When I let n equal 0, my first term in my series is x minus 3 over 6 raised to the 0th power. My second term is x minus 3 over 6 raised to the 1st power. My third term is x minus 3 over 6 raised to the 2nd power, and so forth. If I do a little bit of simplification, we talked about last time how anything to the 0th power is 1, and so this whole expression is equal to 1. So the first term in this series is going to be x minus 3 over 6. No, excuse me, that's wrong. The first term in this series is simply x minus 3 over 6 to the 0th, or just the number 1. The second term is just x minus 3 over 6. And then the third term, and I'm not going to expand it out because, again, my whole job is to find a and r, so I can determine convergence and also find sums. So I'm looking at my geometric series, and it's 1 plus x minus 3 over 6 plus x minus 3, over 6 squared, right? Etc., etc., etc. So what's my a value? My a value, remember, is the first term in the geometric series, and so a is 1. And my r value, well, that's what I multiply by to get the next term in the series. Let me expand again. Remember, in a geometric series, it's a plus ar squared plus ... And I know my a value, that's 1. So the r value is the thing I multiply by a to get my next term. So if a is 1, notice, to get the second term in this geometric series, I would have to multiply 1 by x minus 3 over 6. And so that tells me that my a value is 1, but more specifically also that my r value is x minus 3 over 6, as weird as it seems. I've got to keep that variable. All right, well, we're doing good so far. And our next step now is to figure out when this series will converge. So my geometric series converges when the absolute value of r is less than 1. And so let's play that out a little bit. My r value is x minus 3 over 6. And for it to converge, I need that whole expression in absolute value to be less than 1. And notice this now is coming into a concept from algebra. When I have an absolute value inequality, all right, what I'm talking about is the distance from 0. And so what I'm saying is that this expression has to lie within 1 unit of 0 on the number line. which specifically means, and let me get rid of that bubble so that you can see it again, that specifically means that x minus 3 over 6 has to be a value in between 1 and negative 1. This is an algebra concept, and if you need extra help with making that step to remove that absolute value in that inequality, come by and we'll talk it through, okay? But that's an algebra step. So x minus 3 over 6 has to be bounded by negative 1 on the left and 1 on the right. And so now I have what's called a tripartite or a three-part inequality. And the way we solve this for x to determine what x is going to be is we first get rid of the 6. So I'm going to multiply each part of my inequality by 6. And that gives me negative 6 is less than x minus 3 is less than 6, right? Because that 6 in the middle cancels. And then the second part of solving this three-part inequality, again, we're solving for x, and we want x to be left alone in the middle. So when I have a three-part inequality, the goal is to get x in the middle. And whatever I do to one term, I have to do to all three parts of that inequality. And so if I add 3 to get rid of it in the middle, that means I have to also add it on the right side and I have to add it on the left side. And so what's that telling me? It's telling me that negative 3 has to be less than x is less than 9. This is said to be our interval of convergence for this series. This tells me that as long as my x ranges in between the numbers negative 3 and 9, when I put those numbers back into my original geometric series, I'm going to get a fraction which has a r value less than 1. Okay, so I'm going to get a number in there that's less than 1, and then that means my geometric series will converge. If the number is outside this interval, if x falls outside, well, then that means I have an improper fraction that's being raised to the nth power, and my series diverges. So my interval of convergence is from negative 3 to 9, and your web work asks you to rewrite this specifically in interval notation. So you're going to want to write it as open bracket negative 3 to 9, open bracket again. So let me write down what I have so far. I have that this geometric series is going, well, this series that I have has an interval of convergence, or in other words, converges for x when x is in between negative 3 and 9, or specifically, that's when x falls in the interval negative 3 to 9. Now, the second part of this is to actually determine the sum of the series, but that's pretty simple. The one thing that's going to make it difficult is the fact that it's not quite usual because it's not going to have a number. It's actually going to have letters in this sum. So I'll do a little break right here, but the sum of the series comes from our formula. S is A over 1 minus R, and provided x is in my interval of convergence, the sum of the series then is going to be my A value, which is 1, divided by 1 minus my R value, which is x minus 3 over 6. And if we do a little bit of algebra, that tells me on the top I have a 6 minus x plus 3 over 6, because I'm going to have a minus that's distributed in the top. And I have a common denominator of a 6. So maybe I should work that out a little bit, but I think you guys are pretty good with your algebra. So that means my sum is 1 over 6 plus 3, or 9 minus x over 6. And if I take that denominator, flip it over and multiply, my conclusion is going to be that this sum is equal to 6 over 9 minus x, which came from 1 over 1 minus x minus 3 over 6, right? That's where it came from. Okay, alrighty, 2 problems down. I want to do one more very quickly. I hope this is helping. I hope this helps to spur a little bit of thoughts about how to do these WebWork problems. So let's look at the last example. Okay, so our last example in WebWork that I want to work through is this one here that says you are given that the infinite series n equals 1 to infinity of 1 over n squared is a convergent series and the sum is pi squared over 6. Use this information and your knowledge of series to find the sum of the infinite series n equals 2 to infinity of 10 over n squared minus 8 over 7 to the 2n plus 1. Now, in order to simplify this down, what I want to do is draw on some previous knowledge. Hopefully, well, if you don't remember, it's okay, but there is some knowledge that we have about infinite summations that might have come from Calculus 1 or some other course. And that is, when you have an infinite summation, it often behaves with the same properties as integration. Specifically, if I have a sum or a difference inside of an infinite summation, I can actually separate and look at one term of that summation and then look at the second term. So I can think of it as actually the sum of 2 separate series. And that's what I want to do. I think that's going to help me break down this problem into something that's a little more digestible, a little more clean to look at. So I'm breaking this whole summation into the summation n equals 2 to infinity of 10 over n squared minus the infinite series n equals 2 to infinity of 8 over, and I'm going to rewrite this as I do it, 7 squared to the nth power, or 7 to the 2n, and then 7 to the first. Now, why does that help me? Well, not quite. I'm going to do one more thing. For the first part, that is. In an integral, you know how we pull out constants that are factors. Well, I can also pull out a constant factor from this first series that I'm looking at right here, and I can do that by thinking of this as 10 times 1 over n squared. So I could rewrite that initial series here, n equals 2 to infinity. Instead of 10 over n squared, I'm going to look at it as 10 times 1 over n squared. And I'm also allowed to pull out those constant factors as well from an infinite summation. The second one I could pull out if I want to, 8 over 7. That's up to me. And if I do that, that's going to show me I have a geometric series, or I can keep it in there. That one I'm not as worried about. So I think I'll just keep that, and I'll write that as 8 over 7 times, and then 1 over 7 squared, or 49 if you like, to the nth power. I think that's how I'm going to write that second piece. All right. So now, what does this do? This tells me 2 things. The first thing it tells me is right here, n equals 2 to infinity of 1 over n squared. Well, I'm going to somehow use this given information to help me figure out what this sum is. But it also breaks down and shows me that because I have written this summation over here, this infinite series with the n out here, I have a geometric series, right? That's a clue when the n is in the power that I have a geometric series. And I know what to do with a geometric series and how to find the sum of a geometric series. So it now breaks my problem down into 2 pieces, one of which I'm given and the other piece which I know how to find. So let me start on the back end with the geometric series. I'm going to write out that my geometric series is A plus AR plus AR squared plus ... And my goal is to identify A and R and then find the sum of this geometric series. Now, granted, you have to remember we're starting Don't lose what you're starting at. You're starting at n equals 2. So that means the first term in my geometric series is going to be 8/7 times 1 over 7 squared to the second power. Whew, that's a big number, but okay, that's my first term. My second term is going to be 8/7 times 1 over 7 squared to the third term, to the n equals 3, right? So I started, and I'll just emphasize, I started with n equals 2 this time, and that means now I have n equals 3, and etc., etc., etc. So when I look at my geometric series this way, what is my A term? My A term is kind of ugly. It's 8/7 times 1 over 7 squared, which is just 1 over 7 to the fourth power. Or in other words, my A is 8/7 to the fifth power. Ugh, but okay, that is what it is. How about my R? Remember, R is the value that I have to multiply by my first term to get my second term. And do you notice that to go from my first term of 7 to the fourth to my second term of 7 to the sixth, I need to increase by a factor of 7 squared in the denominator. So pause the video, look through if you need to, but my R factor is 1 over 7 squared. Each time I increase by 7 squared when I multiply each term. All right, so now I notice that my R value is 1 over 7 squared, or 1 over 49, and that definitely is less than 1, and so I know my series converges, so that's good. And then I have to find the sum, and so the formula for the sum is A over 1 minus R, or specifically 8 over 7 to the fifth, divided by 1 minus 1 over 7 squared, and I'm keeping them this way because these numbers are huge, right? That's 8 over 7 to the fifth, and then I have 7 squared minus 1 over 7 squared. And do one more simplification here. So that tells me this sum for this geometric series is 8 over 7 to the fifth times, flip it upside down, 7 squared over 49 minus 1, which is 48. So let me put it cleaner. That's 8 times 7 squared over 7 to the fifth times 48. Ugh, but this is my sum for this geometric series piece. So now the last bit is to use the information I'm given to create this final piece. So I have the sum of my geometric series. My geometric series, so I'm going to put my total sum is going to be something, and then I have my back end, which is 8 times 7 to the second. Oh, I could simplify that down, Tina, now that I see that. Hang on. Let me simplify that down. 7 squared in the numerator cancels with 7 to the fifth in the denominator and just gives me 7 cubed in the denominator. Let me make that a little cleaner. So I have 8 in the numerator, 7 cubed in the denominator times 48. Oh my goodness. And what can I do now? Did you see that? I should have saw that over here. 8 actually divides into 48 6 times, right? Ay. So let me clean that up one more time. So that's going to give me 1 over 7 cubed times 6, or 6 times 7 cubed. That is the sum of the geometric series. Okay, now the other piece. Well, let me do a little thought bubble because I need to think this out a little bit. Let me think this out a little bit, okay? So I know that the summation n equals 1 to infinity of 1 over n squared is 1 plus 1/4 plus 1/9 plus 1/16 plus 1 over 25. Notice I'm just putting n's in for n, right? And I'm putting all my terms and listing them out. And I'm told that whole summation is pi squared over 6. Now the problem is, and do you see the problem? What am I starting with? I'm starting with n equal 2. So really, I only want this piece. This is the only piece that I want out of that infinite series or that infinite summation. That's the piece I want. So how do I get that leftover piece? Well, since the whole thing is pi squared over 6, since the whole thing is pi squared over 6, and I only want that second piece, I think I can get n equals 2, and I'm going to write it down here to infinity of 1 over n squared. That is just pi squared over 6 minus that first term 1 that I don't need, right? I have to take off that 1. And that'll give me the leftover parts. 1/4 plus 1/9 plus 1/16, etc., etc., etc. So that summation, n equals 2 to infinity of 1 over n squared, is pi squared over 6 minus 1. Now, don't forget that factor of 10 in front. So if I take 10 in front of that, this here tells me the summation part. That here, 10 times pi squared over 6 minus 1, tells me the summation part, or the sum of that first piece in my series. So this is the sum of the series, n equals 2 to infinity of 10 over n squared. And this is the sum of the series, n equals 2 to infinity of 8 over 7 to the 2n plus 1. And in WebWork, you need to put all of the pieces together with a minus in between, right? Because there's a minus in between these series to get the total sum. So this is going to be the total sum for my series. Oh my goodness gracious. Well, that was a really difficult and challenging problem, but I hope this explanation helped you figure it out just a little bit and will help guide you as you do your own WebWork problems. Okay, guys, good luck. I look forward to seeing everybody in class tomorrow.